All right. Good afternoon, everybody. Welcome to the 2026 Durand Lecture for Public Service. My name is John Rose. I'm the chair of the AIAA Public Policy Committee, and it's my pleasure to introduce our speaker for today. If you're looking for the lecture on tornado chasing, you are in the right place, so it's going to be an exciting presentation. The Durand Lecture for Public Service emphasizes notable achievements by a scientific or technical leader whose contributions have led directly to the understanding and application of the science and technology of aeronautics and astronautics for the betterment of humanity. This premier lecture is named in honor of Dr. William Durand, who was a U.S. naval officer and a pioneer in mechanical engineering. During Dr. Durand's remarkable 99-year life, he contributed significantly to the development of aircraft propellers, and he was the first civilian chair of the National Advisory Committee for Aeronautics, or NACA, the forerunner of NASA. The Institute's Public Policy Committee takes pride in selecting accomplished leaders in aeronautics and astronautics who can share their knowledge through the Durand Lecture. The 2026 Durand Lecture for Public Service is awarded to a pioneer in unmanned aircraft systems, or UAS, specifically for developing and deploying UAS technologies for atmospheric research. That speaker is going to be Dr. Brian M. Argrow. His lecture is titled Aerospace Engineering for Science and Public Safety, Aerial Robotics to Explore Tornado Genesis. Please allow me to introduce you to Dr. Brian Argrow. Whoop, hold on a second. I get to read your bio first. Sorry, the way it's worded is a little misconstrued. So let's listen a little bit about Dr. Brian Argrow first. At the University of Colorado Boulder, he's a distinguished professor and Glenn L. Murphy Endowed Chair in the Ann and H.J. Smead Department of Aerospace Engineering Sciences. He also serves as Director, Integrated Remote and In-Situ Sensing Program, and Founding Director Emeritus of the Research and Engineering Center for Unmanned Vehicles. He is an AIAA Fellow, and he is also a member of the National Academy of Engineering. He received the Department of the Air Force Exemplary Civilian Service Award for service on the Air Force Scientific Advisory Board. He holds a BS degree in aerospace engineering, MS in mechanical engineering, and a PhD in aerospace engineering from the University of Oklahoma. Today's lecture is based on 30 years of research and development of small aerial robotics, drones. These drones continue to be deployed to increase knowledge of tornado genesis while contributing to public safety by supporting advances in accurate and life-saving methods for tornado prediction, detection, and warnings. We're looking forward to hearing about Dr. Argrow's tornado chasing experiences. If time allows, we'll have a question and answer session after his lecture. Please refer to the QR code, which will be up on the screen here for you to submit your questions. There we go. We'll be using those to have the Q&A. And so now, Dr. Argrow. So now please join me in welcoming our distinguished lecturer to present the 2026 Durand Lecture for Public Service, Dr. Brian M. Argrow.
John, thank you. Oh, thank you to John and to the Public Service Committee for this opportunity to speak about the research that I have been involved in for the past 30-plus years. And you may have heard the Oklahoma connections there, obviously the University of Oklahoma, so it's kind of a natural thing that this might be a topic in which an aerospace engineer from Oklahoma might direct his attention to. So let's get started here with, this is June 10th, 2010, and there's a tornado on the ground there, as you see. This is near Deer Trail, Colorado. And you'll see us pull up here in a second. We're driving relatively fast to get to the south side of the storm so that we can launch our drone. And what you'll see here, that's where we're driving up right there. That's the ground station. So you hear a lot of talk today about BV loss, beyond visual line of sight operations. Well, we were doing BV loss before it was called BV loss. So back in 2010, as you see right here, we're launching the Tempest. And so this Tempest is carrying a meteorological pod, pressure, temperature, and humidity measurement pod underneath the wing. And the students, just before we launched, the meteorologists were saying, you got to get video, you got to get video. And we're saying, well, we didn't get funded for that. And so, literally a student went to a Walgreens and bought a little USB camera, and we taped it on the tail of the airplane. And so what you see in the video there from the airplane is actually coming from a little USB thing. So right here, this is Jack Elston, who is at the ground station. He's talking to our tracker vehicle that's down the road with the drone flying over it. And Jack is now the CEO of Black Swift Technologies. And so Black Swift Technologies, their current claim to fame is that they are providing a new capability to NOAA hurricane hunters. So the hurricane hunters have been launching Black Swift drones in place of the drop-ons that have traditionally been dropped by some of the hurricane hunters. So, and hurricane hunters will come back into this discussion a little bit later. So this is what I'll be talking about. So again, the technologies that have been developed here are traditional aerospace-related technologies. And what I will lay out here is how those technologies have been used to, along with our atmospheric science colleagues, to improve or work on the problem of tornado warning, to improve tornado warning by increasing tornado warning time, not decreasing, but increasing. So we'll talk about the motivation here in terms of why do tornadoes form, and also looking to see how the methods or the data that we're obtaining can be used to improve the modeling and simulation capability, which then will be used for increasing tornado warning. So that's the motivation. Then comes the science. Why do tornadoes form? How do tornadoes form? These are questions that the meteorologists have been trying to address. And in the development of their hypotheses, there are requirements. There are observational requirements that come, and that's where we come in, the engineers, in terms of being able to take the instruments into the places where the measurements need to be made and where you can't put humans in these locations. You can't use balloons because in some instances you're talking about downdrafts and things like that. And you know what happens when you release a balloon into a downdraft? It goes sideways. It doesn't go up. So, and then the technologies. I'll start by talking about the technologies that we have developed and how those are now being used for advancing this area of research. And then the operations. This is probably we'll talk about the technology. Technology is obviously for engineers, that's what we do. Oftentimes we don't work on regulations and things like that, but in the real world, there are regulations that you also have to deal with. And so this is probably the biggest hurdle that we had to face in terms of getting out and making the measurements was the regulatory environment and convincing the FAA years ago to allow us to conduct these operations. And then finally, I'll talk about some of the outcomes. You know, what have we contributed? What do we know now, or what do the meteorologists and scientists know now that they didn't know prior to us putting drones into supercells? So, 2024. So this is the annual report from the National Weather Service on fatalities in the United States, weather-related fatalities. One of the things that jumps out at you right there is, even though I'm talking about tornadoes, look at heat. I think a lot of people don't realize, when we talk about climate change and about things that are happening, take a look at this. If you don't believe the climate is changing, then look at how many people are now in this country where heat is the #1 risk. But you can also see, if we look at the numbers for tornadoes, you can see that even though the numbers are, the 30-year is at 37 or 72 fatalities, that's the average. There are years in which it's absolutely horrible. If you look at the year 2011, that was the year of the Joplin EF5 tornado that killed over almost 160 people. That same, about a month later, There was an outbreak in the southeast, in Mississippi, Alabama, Tennessee. Over 300 people were killed. And so even though these averages tend to smooth out the data, when it's bad, it's bad. And one of the things about the Joplin tornado is the conditions over about a 5-minute period went from not really looking like a tornado to an EF5 on the ground, with people not even knowing that it was just on the edge of town. So NOAA has been working for a number of years on something called warn-on forecast. Now, this is a slide that from former NOAA director Stephen Koch, who has since retired, and he presented this in 2015. And even then, so the focus here is to move away from this warning system that relies on spotters, actually human eyeballs to determine if a tornado, if the radar is indicating a tornado-like vortex, to verify that that's happening with human eyeballs, and to move on to using the modeling and simulation capabilities, the forecasting capabilities, to run ensembles of runs in which the initial conditions are changed just a bit for each one until you get this statistical buildup until you have like the average storm, which is has the highest probability in terms of tracking the progress of the storm. So that's what this warn-on forecast is focused on. And it turns out that they're getting pretty good at it. And this is a success case in last March. This is a case near where the Paducah, Kentucky National Weather Service credits a almost 2-hour warning time or call from to the emergency responders that 2 hours in advance said to be prepared. And so this is a result of years of refining the simulation capability and using in-the-field measurements to validate the modeling and simulation capability. So as early as we actually started the storm research effort at the University of Colorado back in about 1995. It's a whole nother story. I can tell you from being from Oklahoma, let's just say I was at Colorado, and somehow the little drone that had been built at Oklahoma a few years before somehow ended up in Colorado. And so that's a whole nother story. But it's fitting for coming from the Sooner State, where the state papers were stolen from Guthrie and taken to Oklahoma City. I'm not saying anybody stole anything, but let's just say the airplane showed up in Colorado. So, but about that time, I ran into one of the original storm chasers. So if you watch the movie Twister, the first movie, some of the characters there are patterned after people who were real-life characters, and one of them is Eric Rasmussen. And so Eric and I ran into each other at the National Center for Atmospheric Research, and I asked him, what happened to that little airplane that was built? And he told me where it was and so forth, so that's how it ended up in Colorado. But he started a small amount of funding in the late 90s, and we started to build some capability. We didn't really build anything that could fly, but we started thinking about things. So about this, many years later, after meeting Eric, in about 2009, the scientists, the atmospheric scientists were basically saying, look, we need drones. We need to get into these storms. We can't do it with our balloons. Radar, they have very advanced mobile radar, but radar doesn't give you pressure, temperature, and humidity. You have to be there. Now, you can infer it, but you have to actually be there. And then radar, depending on how far away you are from the where you're observing, the volumes in which you are actually resolving the features are relatively large compared to what an in situ measurement might give you. So, continue the motivation. So, what is a supercell? So, if we move from the motivation now to increase tornado warning time to now asking the question, what is a supercell? And how does a supercell produce tornadoes? Now, if you go back, this is an image of the tornado that, as we were approaching back in 2010 as part of the project Vortex 2. And if you look at this, you see the tornado there, you see this cloud. If you can kind of make out in the striations in that lower part of that cloud, that's evidence of the rotation. A supercell persists in part because of rotation. And that is one of the things that differentiates a supercell from a conventional thunderstorm is a supercell is spinning. The entire storm is spinning. It may or may not produce a tornado, but the storm is spinning, and that helps to hold it together. So this is a schematic of what a supercell looks like. So what are the ingredients? Well, the first thing you have to have is wind shear. That just means that as you go up in altitude, the wind is going in slightly different directions. And much like that football there, if you're a quarterback, and I did play quarterback in high school, by the way, but kind of short for a quarterback these days. But if you throw a football, you spin it. That spinning gives it stability, actually, but you're imparting like a shear. You think of that as the rolling motion, and that's what's happening to the air. And as you can see, that from the left side, the wind shear is what produces that updraft, that spinning updraft that you saw. The updraft comes from convection, but the spinning comes from the wind shear. Now, on the front side of the storm, if I go back, just real quick, on the front side of the storm, there's precipitation. And so you see where it says rain and hail. Well, the updraft is pulling these vortex tubes towards it, and some of them are being amplified by the rain that's coming down. The rain is making the air on one side of a tube maybe more dense than on the other, and so it's spinning it. So now you have this combination. You have the main part that's spinning, and then you have this secondary spinning that's coming from the vorticity that's coming in from the front side of the storm. Now all you need to do is pull that up, stretch it, and if you know from a roller skater or an ice skater pulling their arms in, you spin up. That's exactly what the latest information shows us is happening in the storm. So what are the ingredients? 1, 2, 3 steps to tornado genesis. And by the way, tornado genesis is a strange word, but it basically means the process by which tornadoes form. And so you see the streamwise vorticity coming in and spinning up and spinning the storm. Then from the front side, where you have this downdraft, there's an updraft in the middle, there's a downdraft in the front, downdraft in the back, and the one in the front, the precipitation cools that air, makes it more dense, spins it up, and the main rotation pulls that up into the storm. That's how you get the tornado. So the tornado actually is from the ground up. It's really not from the cloud down. It's pulling vorticity from the ground and concentrating it into the storm, to the tornado, as you see right there. Now, that's what I'm saying right here. So you have to have a downdraft you have to have main updraft with downdrafts that will, both on the front side and the back side, that bring in the buoyant air, and that's how you get the tornado. Or you don't. So in this case, you see there's cold air coming in that gets entrained from the precipitation that gets pulled around the backside of the storm. That storm will not produce a tornado. So one of the things that is a focus of the research is not just what are the conditions that do form tornadoes, but what are the conditions that don't, which is the majority of the time. Tornadoes are rare. They're relatively rare when you consider, when you look at supercells, that most supercells do not produce tornadoes. And so this is the case where the birth of the tornado is aborted because of that cold downflow. Now, let's back up. So that's the motivation. We started off with tornado warning, motivation, the science behind the tornadoes that form in supercells. Now let's bring in the engineers. So let's bring in the technology. So the story has to go back a little ways to the early 2000s, so about 2003. The U.S. had invaded Iraq, or Afghanistan and Iraq, or about to invade Iraq. And so the Air Force Big Safari program, I didn't know that one of the professors in our telecommunications department, an adjunct professor, was actually the chief scientist of the Air Force Big Safari program. And so he knew about our work that we were doing, and so they came to us and said, you know, you guys, we know you're working with starting to work with drones and so forth. And so they had a project in which to develop a capability of mobile ad hoc networks using small drones. This is in 2003. So we built a fleet of these aircraft. And so this diagram that you see right here, above that is a photograph of Table Mountain, just north of Boulder. It's a gated off area that belongs to the Department of Commerce. And so we got access to that area, and we built, where we're standing right there, that dirt you see us standing on, that's our runway. We literally took a pickup and put some old fence behind it and drug it along and cleared off some grass and made a runway out there in a gravel pit. So this is our first flight of the Ares. We built this in-house. Students built it, a full carbon fiber, 5 horsepower engine on it. And so here's the first flight. So those just happen to be the only trees out on Table Mountain. and that's where it ended up. And this is the 5th flight. So we built a fleet of those, and we were doing doing voice over IP phone calls, things like that, with where the airplanes were carrying radios and computers, and we had people driving and delivering voice over IP. So we had a successful project funded by the Air Force. That was followed by the first Colorado, well, let me back up. The next major key to pulling this together was Professor Adam Houston from the University of Nebraska-Lincoln. He's a meteorologist there. And he reached out to me when I was director of the Research and Engineering Center for Unmanned Vehicles and asked if he could spend 2 weeks on a fellowship, a faculty fellowship, because he was interested in using drones to measure air mass boundaries, to look at the boundaries between masses of air. I said, okay. So that was the start of a partnership that really has led to what's happening today. So he's a key person there. This was in 2009. We decided that, you know, it's kind of, the students love building the airplanes, but you build an airplane out of carbon fiber and you go out and you fly and it bumps against things and you break them and then you have to put it back in the mold. It takes a lot of time and so forth. Gas engines are dirty, the 5 horsepower engines back then, and they're finicky. You know, you go out on a cold day, we're almost, 5,500 feet there out at Table Mountain. In the wintertime, trying to get a little gas engine to run, sometimes they do and sometimes they don't. And so enter the Nexstar, balsa monocoque airplane that we put batteries in, and this is what we used for our first intercepted thunderstorms in 2009. It was so weak that when it passed the air mass boundary, I was actually in the vehicle looking up at it, talking to the student, Jack Elston, again, who was 2 miles away who was actually piloting the aircraft. And I literally got out of the car, talking to him on the radio, and the airplane's just in one spot. The headwind was so strong, we couldn't get back. And so I talked to him, and he landed it vertically, just like a helicopter. And so I'm standing there on the radio, watching the airplane come right down in front of me, and it's on the ground, the servos are going, it's just still trying to fly, so we picked it up and took it home. So that was our first intercept. Then 2010, this is back to the video that you saw. This is the Tempest. And so if you had asked me what would a storm penetrator look like, I would not have said a high aspect ratio powered sailplane. I would have said a delta wing with a jet, just because of the expected turbulent environment. But if you go to do a search on world record for RC sailplane, what would you guess is the world record for speed? It's over 500 miles per hour, a glider. So if you do, these gliders have been setting records in slope soaring and withstanding tremendous Gs. And I thought, well, this has been recommended to me by our pilot, and it actually worked quite well. So the Tempest is the aircraft that you saw, and this is the Tempest coming home after a mission in, I think we're in Nebraska somewhere for that particular viewpoint. There you can see our mobile ground station with the antenna on top of there. So we had the Tempest. We could demonstrate we could get about an hour of flight time out of it. One of the things we noticed that oftentimes the autopilot would shut off the throttle and it would soar. And so we had a whole side project with the Air Force that was based on the harvesting energy from the environment to enhance the endurance of small aircraft. And so one of the things we did right here is what you're seeing there is a student standing on top of that van there. That van is what's called a mobile mesonet, and it has instruments on it for measuring wind, pressure, temperature, humidity, and so forth. So we took the wing off of the Tempest, put it up there to calibrate, to make sure we could calibrate it. That is probably the worst place you could have a wind sensor, is on the wing. If for no other reason, well, first of all, the wing is generating a lot of lift. And so for those of you who know about circulation, there's a lot of upwash right there at the wing. In addition to the upwash that's occurring, the wing is flexible. I mean, the Tempest is relatively stiff, but it's doing this. So the wings are flapping around, you got circulation right there, so that is not a good place to put a wind sensor, but that's the only place we could because we had the motor in the nose. And so this is showing we use computational fluid dynamics and so forth to compute the offsets and so forth that we were seeing. So enter then the twister. So the twister is basically a two-motor version of the Tempest, and you can see here how we launch it. We launch it off the roof of using a roof rack, and it has the air data probe is in the nose. So so that opened up the ability for us to put that in the nose, and you can see there a glamour shot of the twister as it's about to go back to that supercell that you see back there in the background. Okay, and so the twister was a hot rod. It could fly 120 miles per hour easily, level flight. Okay, and the problem was, though, it was still not conducive to, it's made out of fiberglass and carbon fiber. And again, these things get dinged up. And every time you land one of these on its belly, the next time you fly it, it's a different airplane, okay, because it gets a little bit distorted every time you land it. So we moved on, and now this is the Raven. So the Raven, and I didn't come up with that name. I blame that on one of our students. But it does fit the acronym. This just shows the Raven here that's outfitted with some of the sensors that we fly on it. So in addition to the Black Swift Technologies 5-hole probe, it's a multi-hole probe for measuring wind, we have a custom fine array that's measuring turbulence. We have upward and downward looking infrared thermometers, Visala pressure, temperature, humidity sensors that are generally sent up on balloons. And we also carry internally a particulate sensor that is not pointed to here. So this thing is loaded with sensors. And we get about 2.5 hours of endurance out of a 15-pound airplane, battery power. This shows it being launched. This is you don't have time, when storms are on top of you, you don't have time to put a bungee in the ground. So we developed a catapult launch system that you see. Oh, by the way, did you see this movie? If you didn't recognize it, take a look at that. Okay, so the movie company, when they were developing the movie, they reached out to us and asked if they could make a replica of or if we would have our person who makes our airframes make a replica of the Raven. And so we gave them permission to do it. And of course, when you look at the credits, there is no credit given to the person the company, which I boycotted the movie for 2 months. I kept my $20 in my pocket because I was upset they didn't acknowledge the Chris Click, who his company is Right Wing RC, and so I was pretty upset about it. And but yeah, he called me because he said, Brian, I went to see the movie, and I sat through the whole movie, watched all the credits, and they didn't even mention me. And I said, well, and then they told me I couldn't use anything from the movie, because I asked them, can we make some little, computer covers and things like that? They said, nope. So I said, well, I'll just use it in presentations. All right, so now the hard part. So up to this point, it's been pretty straightforward. Now we're talking about the FAA. So what you see here on the left, that's the COA that's a 25-page application for our first certificate of authorization for a little 5-pound balsa monocoque airplane with a couple little sensors in the wingtips. And so that was in 2008. But that began a relationship. I actually went to visit the FAA in 2004 to talk about, flying drones UAS into storms. And I remember the person I was talking to, he said, come on, let's go out here so we walked outside on the balcony, outside, and he had to smoke a cigarette, and we talked about barbecue and things like that, and then we got back to talking about, he said, you want to do what now? But if you look here at this middle map, those green boxes there, so when we first started, we wanted a certificate of authorization for that big green box. So that's about 200 miles on the side. We couldn't do that because, so we ended up with 59, those little boxes there, each one of those boxes is a COA. And actually for the next star, the COA, the one on the furthest to the east, that single box, that was the first COA that we got, and that was for the next star. And then for Vortex 2, when you saw what we were doing, we had those 59 COAs. And I won't go into all the details as how I had to go to headquarters and was able to talk to them to convert that box, or those 59 COAs, into that green COA you see on the rightmost map. That was our first storm COA, and now you see these other certificates of authorization that go all the way from middle of Texas up to the Canadian border. And we've flown in every one of those areas. This is the concept of operations that for that first movie or video that you saw, where part of going out is to make coordinated observations. So we're not just flying a drone by itself or multiple drones by themselves. We're coordinating this with mobile radar, with these mobile mesonets, and in one case, you'll see here in a second, with a hurricane hunter. So these are what the actual vehicles look like. Those are the mobile Dopplers. The one on the left there is from the farm, which was previously the Center for Severe Weather Research. There's an OU radar down here at the bottom here, the NOXP, and then here's our ground control station, our Scout, which was very important, as I'll say a little bit later, then the tracker vehicle, which was underneath the Tempest as we went into the storm and came out. So the more recent campaign, so Vortex 2 still remains the largest field campaign for the study of tornadoes. And this is the second largest, the Taurus. And this is led by a colleague, Adam Houston. And here on the right, you can see the Raven there in the foreground, and that's Miss Piggy, one of the hurricane hunters in the background there. And so they flew in coordination. So we sat down with the pilots of Miss Piggy and worked out how we would coordinate the airspace. And so they had a display inside of Miss Piggy in which they could see where we were at all times, our location, so they could coordinate against that. This is the area in which we roamed for Taurus. And as you can see there on the right is a schematic that shows the concept of operations. So we were flying 3 drones simultaneously. One was in the out front of the storm, which was measuring the inflow into the storm as Miss Piggy was orbiting the storm. One was going into what's called the right flank, which is at the southern part of the storm there. What that is, that gray area there, is a cartoon of like a radar return for a supercell thunderstorm that has what's called a hook echo. And that little hook there is associated with what's called the mesocyclone. That's the part where it's spinning closest to the ground. And if a tornado will form, it's where all those lines are coming there together. That would be the location where a tornado would form. And so the left flank mission was between the hail, which is on the north side, and the tornado, which is on the south side. So you get in there and get out. That's the idea, with 3 airplanes at a time. So this is day 1. So this is in 2019. This is near McCook, Nebraska. And so we are stopped here because the tornado was about to cross the road. And that's not a joke. That's not a chicken joke. This really was going to happen. But as you see, we stopped, but the tornado chasers, the people who do this for fun, they just blow right past us. They're trying to get. So the Raven is about 2,000 feet above our heads, right in this video right here. I'm sitting in, this is from my cell phone, actually. That tornado had been on the ground for several minutes before that. And so we're closed in, getting measurements. It's hard to see right here, but that's reflectivity that you see in that image up there at the top, and then some of the measurements that we're making there below. Later, there's another tornado intercept you can barely see the, there's a little connection you can see there between the ground and the cloud. That's a tornado near Tipton, Kansas, and we lost video closer in, but as we were heading in, that was one of the perfect setups for us in terms of the sheriff, the local sheriff. He stopped traffic and said, okay, nobody can go on this road but the storm vehicles. And so we had the road to ourselves. We sat, and the tornado was coming towards us, and we just sitting there orbiting, waiting for it to get close, and it got pretty close, and then it dissipated before we had to move. But it was a great case for us. This was a day near Goodland, Kansas, when we had tornadoes all day. And wasn't a particularly good intercept, but if you look here, there's the launch, and so there the guys are loading up the airplane after the first flight. We're going to go move. There's so many tornadoes, they're not even paying attention to the fact there's a tornado on the ground behind them. And so, but later on, the tornadoes get their revenge because as we are driving up this road, our scout vehicle radios to us and said, you guys may want to speed up. There's a multi-vortex tornado forming right behind you there. So we went from chasing to being chased, so we had to get out of there on that one. So, and then this is the last campaign we had for Tornado Genesis to amplify on going into the left flank. So in this case, the concept of operations has changed to where we're stacking the aircraft. So we have one at 2,500 feet, the other at 1,000 feet, and we're going into the left flank to sample with those two aircraft. And therein lies one of the challenges of our group is working on the closer coordination of that. Should be automated. We actually had our pilots, and they're students, they're excellent pilots, but they're managing the flight control systems for that stacked. And here shows the vehicles as we're lined up. This is what we took into the left flank. And our air boss, John Bird, I saw him earlier, he's here who's now at University of Texas in El Paso, and John was our air boss, so he's talking with the FAA while the rest of us are focusing on managing the aircraft, as you can see there. And this just shows the radio communications that we were using in our little armada. We had to have a single pilot for each. We have a pilot assigned to each aircraft. This is the team here that was in those vehicles that you just saw, and most are students. There's a couple of faculty, the one with the long hair in the back there in the middle. It's Eric Frew, he's actually a faculty member, and John is there on the end. I put this in here because this is during Taurus Light. So we're flying into this supercell here with the airplane stacked, and notice, how many rows do you see there when it comes back? There's one road. That's the situation we try to avoid and that road is going south. We're heading south. The storm is coming in from the west. And you notice that lightning strike. See it hit and it lit up those insulators on the power lines there. And so as we're going in, that is one where we ended up having to fly through that precipitation that you see there at the end. That was hail, a mix of hail and rain, because there was one road. And we couldn't turn around and go back because the hail was behind us. And so, but the airplanes came through. Little 15-pound airplanes flying through through something like that. So last thing, some of the outcomes here. This is going back to that first intercept that you saw. This is the track of the Tempest. As you see there, that little, the barbs that you see there, one on the ground and one in the air. The one in the air is with the Tempest, and it shows us intercepting that tornadic supercell. And to the right here is where a composite image, it's kind of difficult to see. I'll see if it's, yeah, you might be able to see that, but that's the image of the Tempest there. The radar is taking that, the radar image here is the NOXP that's sitting over here to the side. And there are other radars and other things along this road, but this is the road here to near Last Chance, Colorado. And this is some of the outcomes. So from that first flight there, this is the trajectory of the Tempest coming in at the FAA limited us to 1,000 feet at that time. And so this was us coming in, and so combining the information that we obtained and with the Tempest, along with the radar data and the ground data from the mesonettes on the ground, this is the pulsing. We were able to capture the pulsing of that tornadic storm as it cycles. And this is the more recent flight. This is the one I showed you earlier near Tipton, Kansas. That was the number 11 there during Taurus. And these are some of the data here that came out that incorporated some of the drone data that we captured. So to wrap it up, so again, we talked about the motivation, tornado warning, increasing tornado warning time, which is now on the order of 15 to 20 minutes. And it hasn't gotten any better in the last, in fact, NOAA made some adjustments in how they define tornado warnings, and it made it look like it got worse, okay? But it's on the order of 15 minutes. The science. So from a pure science point of view, what is it that causes tornadoes to form? And so we're getting a pretty good idea of what that is and certainly the observational requirements. The technology, I talked about the C4 architecture that was adapted from our military, from our Air Force work that we then adapted to do this atmospheric sensing, and then the operations. And I want to give my thanks to the FAA for really sitting down over the years. And I made many flights up to headquarters and also to Denver Center, which happens to be in my hometown of Longmont, Colorado, so I could just drive up the road to talk to those people. And they were very much our advocates, and then the outcomes that you saw there. So the last thing here is the acknowledgments. I will say that Adam Houston, as part of the cuts that you have been seeing in the last few months to a lot of things to do with climate and weather research, his department was cut. And so if you are looking for a top-notch atmospheric scientist, Adam Houston is a person that you should reach out to. And then the other collaborators here, the names you see in gold are students, and the others are faculty and staff. And then there's Chris Click here at the bottom. Last thing I want to say is I wanted to start this out by saying I wanted to dedicate this talk to Mike Francis. Many of you know Mike Francis, and to Ellison Onizuka, who they were classmates, and their senior project in 1968-69 was to design a drone to fly into thunderstorms. And so that continuity at the University of Colorado makes me proud to be able to say that. With that, thank you.
That was fantastic.
All right, thank you.
Okay, let's figure out where we are here now. Okay, so thank you, Brian, for such an interesting presentation. I tell you, there were so many aspects of what you talked about that just started triggering, and you'll see from some of the questions that we got, started people thinking in so many different ways about not only data analysis, but the design of Raven, all sorts of things that got prompted. So it's a really fascinating, it's a great Venn diagram for where all those areas come together. So really excited. So on behalf of AIAA and the AIAA Public Policy Committee, it is my privilege to present you with the 2026 Durand Lecture for Public Service in this medal right here.
All right, thank you.
Oh, yeah, passes. And this certificate.
Okay.
Oh, no problem. Oh, yeah. Okay.
Thank you.
Great. Okay, so we do have a little bit of time left, and so we did get some great questions. We're going to move over to the Q&A part and continue the dialogue. That's great. So as I said, there were some really exciting questions that came in covering a lot of different stuff. So one of the ones that was really popular and resonated, has the data collected, and you talked a little bit about this, produced any major revelations about tornadoes' behavior, or has it been more in improving the predictions of what's happening?
It's more in improving the prediction, the modeling, and it's still the most recent data. It takes time for these data to be digested and written in papers and things like that. But one of the things that appears to be coming out is that it appears that we flew through what's called a stringwise vorticity current. And so this is a feature that became really obvious in some numerical simulations of long track tornadoes.
Okay.
And so it's been a target for observations. And in order to get in there, it sits behind the hail and the tornado, and so it's not easy to get to. And so we actually, there's some data now that shows that we flew through one of those in Taurus light.
Okay.
And so that's an example of some of the things. The verification from Vortex 2, where we flew through that pulsing storm also was a verification. So, but we still got a lot of work to do to get in closer. We're working on making the Raven more waterproof and hail-proof. To something, it can only do so much with hail.
Yeah.
Get in to get some of those more deeper in measurements.
And that was a question that had come up, obviously, a lot of aerospace engineers, was the design of Raven. You talked a little bit about the sensors and some of the challenges of mounting them, but the forward swept aspect of it, what went into designing? Because it's obviously a different environment than you would normally design an aircraft for. So what were the other things you had to consider relative to what Raven looked like and how it functioned?
The forward sweep is actually not a design feature. It was an outcome of working with the manufacturer.
Okay.
And so the next generation of the Raven won't, because that forward sweep really does not add stability. And so it's not an issue in terms of the roll stability we have with the aircraft, but the next iteration of the Raven, it won't have that forward sweep. There's also, it was originally a flying wing.
Oh, okay.
And so that tail that it has on it is to some degree an add-on to give more longitudinal stability. So there, while stability has not been an issue, but we do intend to make it more stable, both by removing that forward sweep and also with working with the tail, the location of the tail. So it's a very stable aircraft. The autopilot has no problem flying it. It's not easy for a human to fly it with sticks.
And so when you think about the next phase of where you want to go, obviously a new version of Raven, but what are the other areas that you're looking to take to the next level? Because certainly, miniaturization and new 3D printing, all sorts of things that are available to you from a kind of a physical standpoint, but what are some of the other things that you're looking to do? And I was thinking about it specifically around AI. Is there an aspect of AI coming into the nature of not only the operations, but the data analysis, the prediction? What are some of the next steps you see coming?
My colleague Eric Frew, he's who has been working with me since 2004. We've been collaborating on the technology side. He is taking the lead on the AI, the collaborative team flights and things like that. We have incorporated machine learning. A few years ago, we developed a flush air data system. And so we didn't put that into the Raven yet, but we did verify with some publications that you can look up that we integrated 12 very inexpensive static pressure transducers into the skin of an airplane, and then used actually CFD to train it. Oh. So we developed from CFD the coefficient of pressure variations and so forth to look to see where the areas of high sensitivity, where we would place real sensors, and then we placed those real sensors there, and we went out and flew it with a well-known or well-established multi-hole probe, and we could get within half a degree of directional accuracy and 0.5 meters per second on the wind speed. Wow. And so getting one of the things that makes our drone relatively unique among the drones that are often used, so you have the multicopters that do the profiling. They don't do a good job in terms of giving you 3D wind. Okay. They can give you some in terms of the horizontal wind, but we're doing 3D wind, and we're actually, back to your question about 3D printing, we're printing our own 9-hole probes now. So we've gone from the 5-hole blacksmith probe to a 9-hole probe that we manufacture in-house. That's our greatest challenge, is accurate wind measurements. Yeah. Because of, it's not only do you have to make the wind measurement relative to the probe, but then you have to go through the coordinate transformations and going from the aircraft to the ground, and the aircraft is bucking around and doing all kinds of things, so it's a challenge, and that's where we're putting I'm putting most of my effort right now is on that challenge of the wind. In fact, we're looking at removing pressure measurements entirely, and measuring wind accurately, totally from inertia, from looking at the GPS and with accelerometers.
Oh, wow. So a lot to go there in terms of development. So obviously the technology is a huge part of what you do, you know, the ability to use a drone, but it comes down to the people also at the end. And so there were some questions relative to the team itself. And people were curious, you know, what kind of students came out for this? Was it, hey, I'm just an aero person, or is it I'm a computer science person, I'm a weather, you know, what was kind of the dynamics around the team that started to form? Because you seem to have a wide variety of people that have been participating. So what kind of drew them to this?
Excitement.
Yeah.
The students, these campaigns, while they can be grueling, I mean, we're out in the field sometimes a month and a half, and you're talking about, and you'll gain 5 or 10 pounds because you're out in the Great Plains, and you know, there are a lot of food deserts out in the Great Plains, and so forth. But the students love the adventure. They love the excitement of being there. So most of them were aerospace students, but we do have students from other departments also. But they're always knocking at the door. And I wish we had more opportunity, more funding to support the students. And many of them are undergraduates. As a matter of fact, the majority of them are undergraduates. And so it's interesting when we're in the field. I'm not the pilot. We have typically an undergraduate is the pilot. He's a pilot, he or she is the pilot in command. And so I have to turn over, when we start the mission, I'm no longer in charge. Yeah. I'm answering to the undergraduate who is the pilot in command.
I just love that, yeah.
I told him, I said, look, you got to get over that. You know,
That's funny. So you showed one of the stats that talked about, you know, when it's bad, it's bad. You said, you know, 500 plus lives lost. So that in itself right there would seem to be, and I don't want to make light of it, justify the business case of why this research is necessary, why, you know, in California they're trying to do, you know, earthquake systems, things like that. What are the challenges that you still face in terms of getting this to the level where it becomes part and parcel of what is, you know, deployed as an awareness system?
Yeah. Well, there have been some decisions made here recently that makes that a bit harder in terms of keeping together the expertise in developing these capabilities. Oftentimes I wish that some people who lived on the East Coast could be transported out into the Great Plains for a year, or to the American West for a year, you know, with the droughts and wildfires and so forth, to see some of these things firsthand, and because that's where this is happening, and it's moving more toward the southeast. You know, Tornado Alley is about to become, you know, it's moving more into the you know, Kentucky, Tennessee, the lower states, and so yeah, so it's not just going to be isolated to Oklahoma and Texas and all those areas, and so other people are going to come under more risk from this. And then as we build, you know, people wonder why these numbers don't go down. Well, we're making bigger and fatter targets. You know, when you have the urban sprawl that you have in cities and so forth, that's just a bigger target for you know, tornadoes too. So this is not something that you can wish away.
Right.
So it's something that you have to prepare for. You have to have building codes and things like that. You know, I born and raised in Oklahoma, and we were always told, I always wondered, why don't we have basements in Oklahoma? Because that's where the tornadoes are. What, you know, people say, oh, it's because of the water. No, it's not because of the water table. It's because the developers chose to do that. It had nothing to do with the water table. Yeah. They chose to build, you know, houses that didn't have basements because it was cheaper. And so that's the kind of thing, though, that you know, that needs to be looked into.
And I think, so this will probably be our last question here, but so the data that you're gathering, obviously, you know, you're using it to help with the predictive nature, but then some of the real world implications, like you said, building codes and things like that. And then I was curious, you know, so what's kind of been the benefit that you've been able to convey in terms of, you know, kind of the physical aspects of it. But then you talked about the early COA process. Have you seen an evolution also that's, hey, we need to make these kinds of things more feasible and easier to do? Are you seeing changes in those adjacent areas, whether it's regulatory or, you know, building codes and things like that as a result of what you found?
I absolutely, and especially when you talk about the FAA, we convened back in 2007, the first symposium on the civilian applications of UAS. We held that in Boulder. I was a co-organizer of that and was asked to do that by NOAA and by NASA. And FAA actually was, well, we brought them in also. And so had a 3-day meeting. There is a paper that we wrote that summarizes the outcome of that meeting. But this is back when when DOE, NASA, and NOAA were all jockeying to see who's going to take the lead in civilian applications of UAS in the United States. And so that process began the discussion. And then us working directly, I spent a lot of time at headquarters, literally sitting across the table from some of the FAA leaders. And I remember one instance where I was talking about, well, our airplane is going to be radio tethered to our ground vehicle as we drive. And so one of the people, he said, well, I saw a puzzled look on his face. He said, well, what about the trees? And I said, well, we're out in the Great Plains, so there aren't that many trees I have to worry about. He said, no, I'm worried. How do you keep that wire out of the tree? I said, no, it's a radio tether.
Some education had to be done.
And he asked it again. And later on, it still didn't sink in, and he asked that question again. And I thought, okay, how can I explain this, that we don't have a wire running to the airplane? So, but that was part of the process, was making them comfortable, because somebody has to sign off.
Yeah.
And I give credit because they work with us, and there's some stories I can tell you about them, giving us a call, saying, "You're doing what?"
Oh man, I can imagine. Well, thank you so much. That was a fascinating presentation. We had a ton of great questions, and I'm sure you'll probably get asked some on the side here as we wrap up. But thank you so much.
You.
A wonderful presentation. That's going to wrap it for today. Everybody enjoy the rest of the week at SciTech. Thank you very much.